In this episode, we will discuss two high availability features. One is ALT, Application Lossless and Transparent, and another one is multi-master. High availability is very important for any mission-critical applications. Any service disruption may lead to big business impact, resulting in financial loss. This is especially the case for the sectors we list here, such as healthcare, finance, e-commerce, telecom, and government. Maintaining high availability is very challenging. Let's look at some of the challenges we are normally facing today. Instance breakdown due to faulty hardware or software bugs. All services require proper operation and maintenance, such as change instance class, add drop instance, switch over, or fail over, or instance migrations. Another new class of challenges are related to serverless. Serverless architecture offers great scalability, more flexibility, and cost less for customers. But service deployment faces unique challenges. Let's look at the right diagram. This diagram shows two instances, instance 1 and instance 2, both on the same host. When the workload increases, it needs extra resource. In the case of the instance 1, since the local has sufficient resource, there's no need to switch over. But for instance 2, there's no sufficient resource on the host. Instance 2 is required to migrate to another host, so we have to switch over. To support non-interruptive switchover, we developed the feature called ALT, Application Lossless and Transparent. Let's look at how does it work. To handle lossless transactions, we need to consider 4 different scenarios: planned short-running transaction, planned non-running transaction, unplanned short-running transaction, and unplanned non-running transactions. There are 4 different activities involved. First, drain session. The first is to wait for the active transaction to end, pave the way for the switch. Second, transaction guard. This is to secure transaction boundary and maintain transaction state, which need to be synchronized from the source node to the target node. Logic transaction ID. This is used to locate the transaction at the target node and execute it again. The last one is the last bit recursor. This one marks the continuation of query breakdowns to ensure that the result set is not duplicated or lost, no more, no less. Now let's look at the GaussDB multi-master. It not only offers high availability, also write scalability, extend from one writer to multiple writers. Here are some of the highlights of the GaussDB multi-master. It is built on existing GaussDB designed for the cloud. And most of key components remain the same, but add the new multi-master functionality. Continuous read and write availability offers 0 RTO, recovery time objective. It combines the best of the lock-based pessimistic concurrency control and optimistic-based design. Each of the approach works best for certain cases. GaussDB makes smart decisions on which approach to use. Here is the multi-master architecture. You can see the overall architecture is about the same as the original architecture we showed in previous episode. They only added the new multi-master service layer. The multi-master service layer has 3 main components. One is Global Slice Manager. It provides a shared view of page slice and mapping. Second, Global Lock Manager manages page lock ownership acquisition and release. And also the Global Conflict Detector. It detects and resolves changes to conflict page update. With additional information, advise master whether to proceed with the commit or rollback changes. Okay, the first demo is to demonstrate the write scalability. We have the running workload against the different masters. Here, we have 2 masters, master 1 and master 2, 2 applications For demo purpose, we use sysbench as application. Application connect to the master through dedicated service port at the proxy level. The proxy will distribute the workload to dedicated master.
This is a live view of the demo environment that I just described. The first tab has windows open to our 3 master hosts, Master 1, Master 2, and Master 3. The second tab provides visibility to our proxy layer. And the third tab shows what's happening at the application layer. We start by showing the masters in our cluster. We have 2 masters and both are active. For demo purposes, we're using the sysbench benchmark to represent our application. As the application progresses, the output of sysbench reports 32 threads connected to the database server, the number of transactions per second, and the number of queries per second. Now we have 2 applications, both running transactions simultaneously connected to different endpoints on the same proxy server. Recall that the second application was mapped to service port 2, which was mapped to master 2. We've shown that 2 demanding applications can simultaneously write to multiple masters in a GaussDB for MySQL multi-master configuration. Each application connects to a logical service point at the proxy layer, and the proxy distributes the application workload to the underlying database masters. This concludes our demonstration.
The second demo is about high availability, the zero downtime for maintenance. In this case, we will have the master 2 will be taken down for maintenance. So before taking master 2 down, we need to disconnect it, and so configure the proxy server, and then no longer to distribute the request to the master 2. In this case, the application will distribute the workload to master 3, and then will take the master 2 down. After maintenance, we bring back the master 2, and then reinstall the connections so that all the requests can redistribute to master 2.
We're looking at our live application environment. I have 3 applications running against the multi-master database. Now I'm going to offline master 2. I type the offline command at the MySQL prompt. This doesn't actually shut down master 2. Rather, we've instructed the proxy to stop dispatching work to it. Now I can verify that master 2 is offline by listing the cluster hosts and their associated service ports. Let's look at the application layer to make sure that this happened. Even though master 2 is taken offline, application 2 is unaffected. This is because the proxy immediately shifted transactions to master 3 as soon as master 2 was no longer available. With master 2 no longer processing transactions, I can shut it down without impacting the applications. With master 2 shut down, I'll recheck the status of the cluster. Note that master 2 has been stopped. This is an important capability. Even though master 2 is stopped, all applications continue to run. Now I can perform maintenance or make configuration changes to master 2, including changing its cloud instance type, all without impacting operations.
This comes to the end of this episode.